if you have a full linear system, that is, if there are relatively few zeros in your matrix, then the normal Gaussian elimination algorithm we presented in the earlier section is probably the best you can do. However, most large applications, nearly always when you have to solve large linear systems in applications, the matrix is sparse. That means mostly zeros, only a few scattered non-zeros, typically maybe only a few non-zeros per row. Now, if the non-zeros are just randomly scattered throughout the matrix, you might think that the Gaussian elimination DLINEQ algorithm we already have would be able to take advantage of that, because when you're adding a multiple of I throw to the j throw, if the element you're trying to knock out is 0, it skips the addition of that row because it's already 0, and that would seem to take advantage of the fact that most of the elements are 0, but in fact it doesn't really, because what's going to happen is if you have a random arrangement of non-zeros throughout the matrix, even if there's only relatively few of them, as you start the Gaussian elimination, by the time you get halfway down the matrix, there'll be so much fill-in that the last half of your matrix will essentially be a full matrix, and so you'll end up maybe cutting the computer time by 50% or so, but not enough to really do much good. We can do a lot better than that. Now, most applications, not all, but most applications that have a sparse matrix, the matrix is banded or can be put into banded form by properly ordering the unknowns and equations. Banded matrix means that all of the non-zero elements are concentrated in and around the main diagonal, within a few elements of the main diagonal, like the matrix we have shown here. If you have a band matrix, then it is possible to take good advantage of the sparseness very easily. Basically, all you have to do is modify your Gaussian elimination algorithm to change the lengths of the limits on the innermost do loops. For example, here in column I, you would only, well, first of all, let's define the bandwidth here. The lower bandwidth n sub LD is the number of subdiagonal non-zero diagonals. NUD is the number of super diagonal. So in this picture we have here, NLD is 2, NUD is 3. So basically you just modify the algorithm so that when you're knocking out the elements below the diagonal, you only go I plus 1 through I plus NLD instead of I plus 1 through N, and then when you take a multiple of the I throw and add it to the J throw, you only go from here through here. And if you're not doing any pivoting, let's assume for the moment you're not doing any pivoting, then the elements outside the band will stay 0. Now, the elements inside the band may or may not be 0. We're assuming they're non-zero, but they could accidentally be 0, often are. But the elements outside the band width are definitely zeros, and they will stay 0 as you do the Gaussian elimination, because, for example, when you're knocking out these two elements, only the elements inside this box change. Because you're adding 0 here and 0, so you skip this entirely, in fact, and you don't bother knocking those out because those are 0. So only the elements in here change. So it's kind of a trivial modification to take advantage of sparseness if the matrix is banded. However, if that's the only modification you do, then you're still not taking advantage of the banded structure as far as the memory. You're wasting a lot of memory by storing the matrix, the whole matrix. You're not wasting computer time because you're only knocking out the 0 elements and only taking multiples of this part of the row and adding it to others, but you're wasting memory. So most band solvers will store the band matrix in a more efficient form, like the band solver dband in the book stores the band as a n by NLD plus NUD plus 1 array, and basically the first column, the first diagonal here becomes the first column, the second diagonal is the second column, and so forth. So the matrix is stored by diagonals rather than by columns, and that way the stuff outside here which is never going to change, always going to be 0, isn't even stored. And you've saved memory as well as computer time. Of course, that complicates the algorithm somewhat because of the way the matrix is stored, but basically it's just the standard Gauss elimination algorithm with advantage taken of zeros outside the band. Any zeros inside the band will be not taken advantage of, and the matrix is stored in an efficient diagonal form. Now that's all assuming you don't do any pivoting. If we have to pivot, and normally we will, then that changes things a little bit. Then it's no longer true that all the elements outside the band stay 0, because, say in the worst case scenario here, you have to switch this with that, then that brings a non-zero up here. When you switch these rows, then you're introducing some non-zeros up here, and then everything inside this box is now going to change, or could change in the worst case. So, but notice that the elements below the band still stay 0, and all you've done is added another NUD non-zero diagonals here, and so for a large system, when n is large but the bandwidth is relatively small, it's still quite efficient. For example, a tridiagonal matrix where NLD and NUD are 1, you start out with just 3 diagonals. If you have to do pivoting, you have to keep up with 4 diagonals. It's still much more efficient than using full Gauss elimination. Actually, there are other direct solvers. Direct solver means basically just Gauss elimination, possibly with advantage taken of zeros. There are other direct solvers that can take a more general sparse matrix that isn't banded and solve it using Gauss elimination very efficiently, but they're quite complicated. They're beyond the scope of this course. So basically, if the matrix can't be put into banded form, then it isn't easy to take advantage of the sparseness. However, then there's another class of methods called iterative methods that take advantage of sparseness, that solve linear systems, and they have an entirely different philosophy. That's not based on Gauss elimination at all. They're iterative methods. That means that they never find the solution exactly. Direct methods find the solution exactly in a finite number of steps. Iterative methods just keep getting closer and closer to the solution, and they're not designed for just arbitrary linear systems. In fact, the ones we talk about in this book won't even work at all for any linear system that has any diagonal element of 0. The 3 iterative methods that are discussed in section 1.8 will all completely break down if any diagonal element is 0. So they're certainly not designed for general sparse systems, but they're designed for certain important applications, particularly solving partial differential equations with either finite difference or finite element methods, but also useful for other types of problems. I won't go through the theory on convergence and so forth. That's in section 1.8. You should look at it, but all I want to do is show how they're used in practice. So here's a typical problem where iterative methods are useful and very useful. Solving a partial differential equation, we approximate the partial derivatives using finite differences, and we end up with basically this linear system here. Now there's actually m minus 1 cubed unknowns and m minus 1 cubed equations, because I, j, and k each go 1 through m minus 1, and m might be large. The bigger m is, the more accurate our solution will be, so we may want to solve really huge systems here. For example, if m is 10, then we're talking about 9 cubed, 729 unknowns and 729 equations. But notice that each equation has only 7 unknowns, at most 7 unknowns. There's 6 on the diagonal and 6 minus 1 scattered across the matrix. The 3 iterative methods that are discussed in this book are very simple when applied to a problem like this. all three of them, you basically just solve the ith equation for the ith unknown. In this case, since we're using a triple subscript here, we should say rather that we solve the ijk equation for the ijk unknown. Anyway, we solve this equation for that unknown. And we get this. And the Jacobi method, all in the world you do is make an initial guess for all of your unknowns, plug those in here, and calculate new values here. And it's obvious that if this converges, it converges to a solution, because if eventually plugging in old values here and calculating new values here doesn't change any of the u's, if uijk n plus 1, superscript n plus 1 is the same as uijk n, then that's a solution, because this is equivalent, this is satisfied exactly then if you take off the superscript, and that's equivalent to the original system. So clearly, if the Jacobi method converges, it converges to a solution. Will it converge or not? Well, certainly not for all linear systems. It's shown in the book that this converges if the original matrix has what's called diagonal dominance, which basically means the diagonal element in each row is bigger than all the others in absolute value combined. And, well, this one is almost diagonal dominant. It's actually weakly diagonal dominant, because remember, we had a 6 in the main diagonal, and at most 6 minus 1s, so it's not quite diagonal dominant. It's weakly diagonal dominant, but it's also positive definite, is shown in the book that this is positive definite, and we also prove that positive definite system, the Jacobi method, well, actually, not the Jacobi, excuse me, the Gauss-Seidel method will converge. Gauss-Seidel method is a slight modification of this. In fact, if you try to program this and you're not very careful, you may accidentally program the Gauss-Seidel method. Let me show you in the program. The program is remarkably simple for the Jacobi method's remarkably simple. Here's the whole program. Basically, the rest of it is just checking for convergence and setting initial values and stuff, but it's basically here. Each iteration, you simply take old values for all your u's, whether they're on the boundary or not, calculate new values, and you just keep going through that over and over until it converges. Now, if you just put, instead of u old here, if you put u, and if you use u instead of u new, that's actually the Gauss-Seidel method. In fact, as I said, sometimes a student tries to program the Jacobi method and accidentally programs the Gauss-Seidel, because the Gauss-Seidel simply it doesn't insist on waiting until the next iteration to update the right-hand side values. So this is almost exactly the same as the Jacobi method, except that we had u olds here and u news here, and here they're all u's. Let's go back to the original equation here. If you actually put in, you define values for all the components of u at the 0th level, and then you calculate all the values on the 1 level, then you put those in on the first level and calculate the second level. That's the Jacobi method. Gauss-Seidel, you use the latest available values here. In other words, why wait for the next value of ui minus 1 jk? If you already have a later value, you simply use it here, and that's the natural way of programming it. So the Gauss-Seidel is basically the same as Jacobi, except that you use the latest available values on the right-hand side instead of the values from the previous iteration. Instead of insisting on the values from the previous iteration, you simply use the new values as they become available. And that, as you might expect, normally converges a little faster. Why should you wait if you have a better value? And we show in the book that for positive definite systems or diagonal dominant systems, Gauss-Seidel is guaranteed to converge. Jacobi is guaranteed to converge if it's diagonal dominant. Then there's a third method, which is actually an order of magnitude faster than Gauss-Seidel, that's almost identical to Gauss-Seidel, but one slight difference is kind of an extrapolated Gauss-Seidel. The new value of u at each point ijk, you calculate this, which would be the Gauss-Seidel value, and this is the old value, so this is like the new Gauss-Seidel value, this is the old value, and you take a weighted average, except normally W is greater than 1, so this is like an extrapolated average. It turns out that this converges much faster for the type of problems that we're interested in, for positive definite problems. So all three methods are extremely simple to program. Here are some results for SOR and Jacobi and Gauss-Seidel. Here's Jacobi method, here's Gauss-Seidel, and then these are values of SOR with other values of omega. Now the parameter omega, it's discussed in the book how that's chosen, but as you can see here, there is an optimal value. It's usually difficult to know what the optimal value is, but typically it's between 1 and 2, and most any choice between 1 and 2 will do better than Gauss-Seidel. For example, with m equal to 20, then you have m minus 1 cubed unknowns, which is 6,859 unknowns. It takes Jacobi method 1,920 iterations to converge to certain accuracy. Gauss-Seidel takes exactly half as many iterations, and SOR takes about 7 times less with this value of omega, and even if you don't use optimal value of omega, it still will do generally much better than Gauss-Seidel. We're not going into the theory in this video, but it's discussed in the book. So the bottom line is the SOR program, which for these types of problems is actually much faster than Gauss elimination or even a band solver, is remarkably simple. There's the whole program, and a lot of that is just calculating the residual to see when it's converged. That's basically the whole program there. Calculate the Gauss-Seidel value using the latest values on the right-hand side, and, well, actually this is Gauss-Seidel, but if you replace that by the statement back here, then you have SOR. Finally, the last homework problem in Chapter 6 is an interesting one. Involves solving a linear system which is very sparse. It's a very sparse system, 20,000 by 20,000 linear system, only about 15 non-zero elements per row, but yet it's not banded, and I don't think it's possible to put it in a banded form. And you're supposed to solve a linear system. Well, the obvious method of choice here has to be an iterative method, and in fact the iterative method will work quite well, Gauss-Seidel.